We prepared a graph representing water to show energy changes, kinetic and potential, with temperature. We'll start with the solid phase, using ice as our solid. When water freezes, it forms a three-dimensional structure that prevents the water molecules from getting too close to one another. Each oxygen atom is associated with 4 hydrogen atoms, 2 by covalent bonds and 2 by intermolecular forces. The covalent bonds are shown by the solid lines and the intermolecular forces by the dotted lines. Intermolecular forces are unusually strong in water due to hydrogen bonding. The energy required to overcome these strong attractions is evident in water's relatively high melting and boiling points. For example, methane, made of molecules of similar size and mass, has a melting point of minus 183 degrees Celsius and a boiling point of minus 161 degrees Celsius. The steady addition of heat to frozen water causes the molecules to vibrate more, which raises their average kinetic energy. The kinetic energy of water molecules in an ice crystal is the result of the vibrational motion of the whole molecule as well as the vibrations of the hydrogen and oxygen atoms within each water molecule. As we continue to add thermal energy, the motion of the molecules becomes progressively more vigorous, and the temperature rises accordingly. At the melting point, 0 degrees Celsius, the intermolecular forces are no longer strong enough to withstand the violence. The continued application of thermal energy is now used to overcome the forces that lock the ice molecules together into the solid. As a result, potential energy increases. This increase in potential energy causes a phase change, solid to liquid. Notice that the temperature of the substance does not rise during the melting, since the added thermal energy is converted to potential energy. The energy absorbed to melt 1 mole of ice is called the molar heat of fusion. Let's now examine the energy changes in the liquid phase. Once all the solid has melted, the further addition of heat causes the average kinetic energy to increase again. The molecule's vibrational motion, as well as translational motion and rotational motion, increases. We measure these increases in kinetic energies as an increase in temperature. At the boiling point, 100 degrees Celsius, the temperature does not rise, so we know that the average kinetic energy holds constant. Now the added energy works against the intermolecular forces, which hold the molecules together in the liquid. The molecules then separate, storing the added energy as potential energy. Free of these intermolecular forces, the molecules fly apart as a gas. Once again, since the temperature of the substance does not rise during melting, the added heat increases the potential energy of the molecules. A phase change has occurred, liquid to gas. The energy absorbed per mole of water during boiling is called molar heat of vaporization. After the phase change of water liquid to water vapor, the temperature rises again as the added heat increases the average kinetic energy of the gaseous molecules. Notice the plateau at the boiling point is longer than the plateau at the melting point because it takes almost 7 times more energy to vaporize liquid water than to melt the ice.